All right, so now that we know how to take derivatives, we know how to compute directional derivatives, we can compute the growth at any direction. We can try to figure out where are the maximum values and the minimum values on our graphs, just like we did in Calculus 1 with functions of one variables, except that now graphs are three-dimensional, and there is a lot more brand new possibilities. So for example, in this function, there's going to be some absolute max, some absolute minimum value, but then there is also local mean, a local min, a local max, and there is also a point here that is not clear, but in one direction is growing, in the other direction is decreasing in both directions. So there is going to be several types of critical points that we're going to have to try to separate one from the other. And that's what just like in the one variable calculus, the second derivative test helped us try to understand what kind of critical point we're dealing with. So how are we going to tell critical points? Just like in the, how did we do it in one variable? We knew that the critical points, the possible maximum values and minimum values happened where? They happen where the tangent line is parallel to the x-axis, right? So the same thing happens here, that if I want to know where there could be a possible absolute max or a local max, those will happen in places where the tangent plane is parallel to the xy plane. And similarly here, or here, those are all the points where I want to know what is happening. However, that plane is also, at this point, the tangent plane is also horizontal to the xy plane. So the tangent plane alone can't distinguish if I have really a local max, a local min, or I have what's called a saddle point, where in one direction it's a local min, but in the other direction it's a local max. So that mismatch in two directions, getting a local max, local min, gives you this shape, which is some sort of like saddle point, and these happen in many places. For example, in here, as I said, there is also a saddle point right there and right there. Now, how are we going to tell these points apart? We want a tangent plane that is parallel to the xy plane. So we want a tangent plane that the normal is parallel to the y-axis. We know what is the normal direction to the tangent plane is given by, in 3D, is given by this gradient vector that we saw before, which is the partial with respect to x, partial with respect to y, minus 1. And I want this to be parallel to 0, 0, 1. So what I need is actually for these two derivatives to be 0. So we're going to have critical points when this happens, and those are going to be the points that are going to be like that, and then we're going to have to try to decide if those points are local maximum, where every value of the function nearby the point, the value at that point is larger than any other value, or that we have a local minimum, and every point in here is lower in value, if that point or that value is lower than any point nearby. And then we're going to have things that, well, they're not either local min or local max, but the partial derivatives vanish anyway. So as I said, that's a theorem that to detect local max or local mins, we have to find places where both partial derivatives vanish, which are the places where the tangent line, the tangent planes become parallel to the xy plane. And we are going to call those critical points. So those points where the gradient vector of f of little f is the 0 vector, so where both partial derivatives vanish, we're going to call those critical points. So let's do an example of finding, first of all, what are the critical points of this function. And then we'll do some work, maybe next time, trying to identify what kind of critical point we're dealing with. So I want points such that the gradient vector becomes the 0 vector. Okay? So the gradient vector is the derivative of f with respect to x, derivative of f with respect to y. So let's compute derivatives. With respect to x is 2x minus 2. And with respect to y, it is 2y minus 6. And if I want these two to be 0 simultaneously, that has to be when x is 1, and this has to be when y is 3. So this tells me that there is exactly one critical point which is precisely the point 1, 3. So there is only one critical point here. There can be one, there can be none, there can be infinitely many critical points. So we're going to see that there's a lot of possibilities. And why is there one critical point at that point? It's because the graph looks exactly like this. It's a paraboloid with vertex above 1, 3. How do I know that? Because I can complete the square of this quadric. So if I set this z equals to that, this is a quadric surface, the graph is, and I can actually complete the squares to show that this is equal to x squared minus 2x. I completed to x minus 1 squared. And the other, in y, I would complete it to y minus 3 squared. And then from here, I would get a plus 1, plus 9 is plus 10, but I have 14, so I need a plus 4. So you see that this shape is a paraboloid that has been shifted to the point 1, 3 and lifted up 4 units to get the paraboloid that is in the image. And that's why that point is coming up as critical, because yes, the tangent plane at that point is parallel to the xy plane, and we're going to have a global minimum at that point. And I can evaluate at that point f of 1, 3. Now that it's in this shape, I see that this is 0, 0 plus 4. So this is the global and local minimum value of the function, and the smallest possible value is 4. Any questions on how I completed the square? How am I completing squares to simplify the formula for the graph? All right. So now we're going to do a second derivative test for two variable functions. Just remember how it worked in the one variable case. So suppose I have this and this. At this point, I have critical values. The tangent line becomes, at those 2 points, those two functions have critical values because the tangent line becomes parallel to the x-axis. How do I tell that one is a local max and the other one is a local min? By looking at the second derivative. Because here, the tangent line from left to right, the tangent line is losing a slope. The slope is decreasing, while here, the tangent line from left to right, the slope is increasing. So that means that here, the second derivative is, the rate of change of the first derivative is negative. So the second derivative must be negative on top of the first derivative being 0, while here the second derivative is positive while the first derivative vanished, right? So using this test, we could tell in one variable if we have a local max or a local min. So we have something similar in 2 dimensions. And actually what we do, where this formula comes from, you should think about this as, you know, in this comes up like in the quadratic formula, you know, minus b plus, this is the wrong color, minus b plus minus the square root of b squared minus 4ac divided by 2. That is similar. This is sort of like an ac minus b squared divided by 4 kind of thing, that formula over there. And it comes from, instead of considering a tangent plane, we consider a tangent surface, a tangent quadric surface, to see what is the best fit at that point. If it's a paraboloid that opens up, is it a paraboloid that opens down, or is it a saddle point? And then we compare to our own graph. But in any case, this formula right here, this quantity, tells you what is happening. It's the equivalent of the value of the second derivative in the one variable case. If this capital D, if this value of second derivatives is positive, and the second derivative with respect to x is positive, then we have a local min. If it is positive, but the second derivative with respect to x is negative, then we have a local max. And if this is negative, then we have a saddle point. So we will use this next time to compute some, to analyze some critical points.